This meeting is being recorded.
All right. Okay. So good afternoon, everyone. My name is Danny Shaw. Welcome to the engineering seminar series hosted by University of Wisconsin-Platteville. The engineering seminar series are 1 hour long presentations of real-world projects that showcase the plan, design, construction, maintenance of engineering projects and how they contribute to our community. Attendees are also eligible to earn 1 professional development hour. All seminars are free and open to the public. To minimize the background noise, all attendees are muted during the presentation. Please use the chat box to ask questions during the presentation. And at the end of the presentation, we will have Q&A sessions, and then you are free to unmute yourself and ask questions and then join the discussion. So today we're very excited to have Paul Croker coming from AIRS Engineering to give us a presentation about the unmanned aircraft system. So it's very exciting topic. I was actually looking at the field trip on Thursday because our bus will be right between the Artsman and then the stack of the tallest structure on campus. And then I was searching that, and then I found AIRS was the company who did the inspection on all the stacks at UW campuses, UW system, including La Crosse, Eau Claire, Madison, and Platteville. And then I learned that Platteville, the stack we have, is 220 feet tall, built in 1964. The last survey was done by AIRS in 2019. So Paul, are you aware of that project? The project I'm talking about?
Yeah, I'm familiar with it. I have some pictures from projects like that tonight. So
awesome. Yeah, I just learned that today, just by accident, because I was searching something else and I found it. Oh, wow, okay, cool. Anyway, this seminar is sponsored by AIRS. Thank you for the sponsorship. So let me do a very quick introduction of our speaker today. Paul is the program manager for the Unmanned Aircraft System program at AIRS. He completed his master in forestry with an emphasis on GIS and remote sensing technology at Michigan Tech University in 1999. Since then, he was touched on many aspects of geospatial technology, ranging from imagery-based expert system at Stennis Space Center, Mississippi, and Signature Research Incorporated in Michigan, to developing the and managing an enterprise GIS and unmanned aircraft system program for the Menominee Indian tribe of Wisconsin Forest Management Program. His current role at AIRS centers on rapidly growing the geographic footprint and sophistication of AIRS UAS capability in support of survey and engineering projects. So again, we're very excited for the topic. I personally very interested in this one. My childhood dream was to be a pilot. So I'm a little far from that, but nowadays you know that, right? For those who are interested in drones, you can become a pilot. You actually get license. You have to get license to fly legally, right? So to be honest, it's on my list of considering. So, but right now too many things going on. But anyway, please help me welcome our speaker. It's all yours.
Well, thanks everyone. And first of all, I regret that I couldn't be there in person tonight. I'd fully intended to. We're in the middle of launching several projects right now in multiple states, and I have a new flight crew on their way to North Carolina as we speak. So I was pretty tied up with that today. So appreciate the opportunity to speak with you though, and share some experiences that we have and kind of give you a little bit of insight in how UAS is impacting the civil engineering industry. So Dr. Zhao already gave you an introduction of myself, so I can probably move on from that. But, maybe just really quickly, just to touch on my background as a natural resources and forestry, but I've been using geospatial technology throughout my career in a variety of different roles, everything from natural resources to the defense industry to now civil engineering. So when you get into geospatial technology, that touches on every aspect of what we do. And what we see at AIRS is from the engineering and survey standpoint, UAS is a really good fit with that as well. Just a really quick overview of what AIRS is if you're not familiar with it. So it's an engineering firm that was established over 60 years ago in Eau Claire. And since then it's grown to over 300 employees. It's employee owned, which is fairly unique in this industry. So architectural, engineering, construction. And we have offices, several offices in Wisconsin. We have some in Colorado, Florida. We have several offices down there. We have folks in North Carolina and now in California. We recently acquired a mechanical, electrical, and plumbing firm out of California. So we've added that, and it fits really well with our architectural and civil engineering. And we work on a variety of different types of projects for folks across the region, across the country. Relevant to your interests, I'm sure, would be the civil and municipal engineering with transportation, structural design and inspection. We have a very robust staff of river engineering, water resource management folks out in Fort Collins, Colorado office, as well as our architectural division. And I work with the geospatial division, which is as an aerial mapping group and a couple of survey groups based in Wisconsin, mobilize often to projects out of state as well. And the projects that we work with out of, I'm specifically with the survey groups, is providing support, data acquisition support to clients, both external clients that come to us, as well as our engineers on staff that need survey data, aerial mapping data that we can provide with UAS to support them in their engineering projects. So just a really quick discussion of what we're going to talk about tonight. I want to go back and give a little bit of background on UAS as a whole. And by the way, my slides even call it unmanned aircraft systems. In the spirit of inclusion and diversity, that's rapidly becoming uncrewed aircraft systems. So you'll probably see that as well. So I need to train myself to use that term from now on. It's been widely adopted by many folks in the industry. But I want to give you a little bit of a background of where UAS has come from and where we are today. So it's rapidly changing, and it's impacting a lot of, in this case, engineering projects and providing more and more capabilities that we can use on them. And I'm going to discuss that gradient of capabilities that are available using UAS, from the very simple end to complex survey level measurements on the upper end of it. Spend a little bit of time, not much though, talk about mission planning and risk mitigation. And the reason for that is to give you a little bit of an understanding of what goes into using UAS on projects. And then I want to spend the majority of the time showing different examples and discussing ways in which we've used this technology to aid our engineers in conducting their work. So first, why are we using UAS to begin with on these types of projects? So one way to think about it is UAS fills a gap that kind of sits between conventional ground and pound survey work on maybe the smaller end or the very detailed end. And on the other extreme, when you start talking about countywide or even regional imagery with traditional manned aircraft. So UAS kind of fits in the gap in the middle there. So both in terms of size and in complexity of projects. So oftentimes we find it's an economical middle ground for collecting data on sites that might be really time consuming or expensive to do a traditional way, or there may be a little bit on the small end where you don't want to mobilize an aircraft from hundreds of miles away to go fly a 40-acre site, for example. From the imagery standpoint, it provides a unique perspective, obviously, from the air of a project site for project monitoring. We'll show some examples of that here in a little bit. And from a survey standpoint, it provides a safe data acquisition alternative on hazardous sites. So I'll show you a site on a busy highway in Milwaukee in which we acquired some data using UAS that eliminated the need to have surveyors closing lanes on a really busy highway overpass. So a little bit about where UAS has come from. So unmanned aircraft essentially have been there since the beginning of flight itself. So as long as people have been putting aircraft in the air, they've been tethering balloons with sensors and eventually towing gliders for targeting. and gunnery practice, and eventually having better control systems where we could fly aircraft remotely for a variety of aspects. Early on, most of this adoption of this technology and the advancement of it was spearheaded by military needs and through government activities. So as we see with the advancement of flight itself, so there's a lot of money poured into it. So there's a lot of resources and big complex systems that fulfilled the needs of the military for their various uses. More recent years, within the last decade or two, a lot of this has been miniaturized sensors have been developed for the civilian sector and adapted in a way in which they're more cost effective. So we're no longer talking about multi-million-dollar platforms. We're talking about, in some cases, something you can pick up at Best Buy. So there's been some key technological breakthroughs that allow this, as well as just equally as important is the streamlined regulatory process that allows us to fly international airspace for commercial data acquisition. So that's an often overlooked point right there, because prior to this, anybody that wanted to use a drone for data collection had to follow a lot of this very rigorous regulations that were in place for traditional crewed aircraft. And that was a very high hurdle for smaller organizations to be able to fulfill their needs using a drone. So some of the innovations in aircraft are things like GPS. Kind of take that for granted today. But prior to having GPS for stable flight, it required humans in the loop to constantly be correcting the flight of an unmanned aircraft. Things like improved battery life and hybrid power systems have allowed us to keep aircraft in the air longer, power them and carry heavier payloads, and be able to use them in a cost-effective manner compared to a larger aircraft that would have a combustion engine on board, for example. There's been a lot of advancements in safety that allow us to use drones more safely in the airspace. Things like collision avoidance. There's a new thing coming out called remote ID that allows law enforcement to be able to start to enforce some of the regulations a little better when all aircraft are required to have basically a transponder that they can ping on board and see who is flying an aircraft that's within an area to ensure that they're following the regulations. Another important innovation has been redundant systems that allow fault tolerance on the equipment that we use, so that in the event of an electrical or mechanical failure or a communication failure with the ground control station, the aircraft can still be flown safely. Some of the newest innovations that we're seeing now, probably the next big revolution in drone technology that you're going to see, are advances in flight control systems that integrate AI for assisting in the flight and improving sensors that can control the flight. For the most part right now, most UAS operations are within what we call visual line of sight, and we're going to go over the regulations here shortly that will discuss that. And that is because we don't have a pilot on board. We need to have somebody that has visual line of sight to that aircraft to make sure that we're not conflicting with other aircraft in the airspace and endangering anybody on the ground. So combining redundant aircraft systems along with AI-assisted flight to be able to help see and avoid other aircraft in dangerous situations will allow us to do things like beyond visual line of sight better, as well as operate in GPS-denied environments. So, for example, if you want to fly inside of a stack, like Dr. Zhao mentioned, or do a bridge inspection underneath the bridge where you may lose GPS, you want to have some other control system in place that can control that drone when you lose GPS. So those advances are rapidly coming about now to make these systems even more reliable. Some of the sensor innovations include better cameras. So having a 4K camera, just like it's on your phone standard now, it's the same thing on the UAS. A couple of years ago, that was something you'd buy up to. That wasn't standard. So it's just accepted now with the miniaturization of cameras and cell phone technology. That technology is also being passed along to the UAS industry. There's also a lot more choices for sensors in general. So better zoom cameras, multi-band, meaning you can look into bands beyond visual electromagnetic parts of the spectrum. So infrared, near infrared, as well as thermal infrared, hyperspectral. and metric grade cameras. So a traditional aerial image that you get from a large camera on board a plane has very well-known tolerances and focal lengths and characteristics of the lens that give you a much higher quality image than you can get from even like your cell phone, or a lower grade drone image. And that's essential if you're going to be making accurate measurements from it. So a metric camera option is relatively new in the US as well. There tend to be heavier cameras, so you need a larger drone to carry it. Another one that we're going to look at a lot here tonight is LiDAR. So using LiDAR to scan construction sites, buildings, infrastructure, to be able to get accurate measurements from a point cloud is proving really valuable in the area of survey. We also use it for mapping infrastructure in an as-built situation as well. So LiDAR is becoming more and more powerful on a UAS platform. We have better choice of IMUs. An IMU stands for an inertial measurement unit, and that basically it's a sensor on board that tells you the roll, pitch, and yaw and the direction an aircraft is moving. And that's essential if you're trying to work backwards and figure out what you're shooting at with a LiDAR to be able to get a very accurate XYZ location of those points. So all this technology is rapidly evolving to give us increased accuracy, better results, and higher point densities in point clouds. And all this is coming with a reduction in size, weight, and power consumption, allowing you to fly bigger areas within a mission. Generally, whether you're talking about imagery or LiDAR, you can look at this as a capability gradient. So on the lower end, this is something like you could buy at Best Buy. You could get a DJI Mavic drone, and you can get some decent imagery and video from something like that. From a survey standpoint, they're relatively limited because they have lower accuracy. It's not a metric grade camera. You can move up in level to a higher grade camera or LiDAR sensor that allows you to get what we call mapping or asset grade. So this would be something you could put into a GIS that would be a good relative accuracy for planning on a site level, but it's not something you could design from at an engineering level. It's not survey grade. You go a step higher and you get to a survey grade sensor where you can get, for example, with an elevation on a LiDAR point cloud plus or minus 2 centimeters, sometimes even better than that. You could get even further with a LiDAR terrestrial scanner. So like a survey total station that's on site that's scanning for several minutes in one place from a known XYZ location, that would be even a little further on this gradient. So in the UAS world, I'm not aware of any sensor that can quite touch a terrestrial scanner. So you could put that on the upper level of this, but the downside of terrestrial scanners is they can't cover a big area. You set them up on a point and they scan, and you got to pack it up, move it to another point, scan, and so on. So the advantage of UAS is if you can get by with that level of accuracy, is you can scan a fairly large site in a short amount of time and gather a ton of data. As far as the regulations go, I kind of touched on this a little bit. The FAA, Federal Aviation Administration, regulates the national airspace. So that's anything that's flying above the surface of the earth. So there is no height limit altitude to that. You have to operate in the national airspace and follow their rules. And that's done for safety reasons. So traditionally, they look at 3 different areas. Look at this Venn diagram here of how these things overlap with each other. They regulate aircraft. So they have what they call type certifications. So they have known component failure rates on an aircraft. So they can assure relative reliability of the aircraft, that it's not just going to randomly fall out of the sky. So any kind of an aircraft that you buy that's not experimental has to follow these regulations. They also have pilot certification. So pilots have different ratings based on what they're flying. So UAS is one of those ratings. And that dictates the qualifications that you have to meet to be able to legally fly within that rating. So if it's a manned aircraft, it might be single engine rating in daylight, or instrument ratings, multi-engine, passengers, and so on. The third sphere is operations. Call it ConOps, your concept of operations. And that dictates how you're able to fly that combination of aircraft and pilot and do so safely in the ways in which you operate that and where you're operating it. So the different types of airspace that you might encounter have different rules and how you can fly it. So the way the FAA really dealt with this kind of cleverly in 2016, because prior to that, anybody flying drones had to deal with all three of these different areas, is they took aircraft out of the equation. They said, we don't have to do type certification because that's really expensive. If you want to certify all the parts on a drone and ensure that they have a really low failure rate, and anytime you want to upgrade it, you got to go through this entire expensive process again, it becomes really cost prohibitive to have a drone that costs a couple $1,000s for an engineering firm or a photographer to own. So what they did is they focused on pilot certification and ConOps. And under the ConOps, they gave us a set of rules that we can fly safely with looser restrictions on aircraft reliability. So don't fly it over people, keep it under 400 feet. And there's a handful of other rules in there, but those are the big ones to ensure that if you do have a failure, it's not going to come down on somebody and hurt somebody. And it's not likely to encounter any aircraft at 400 feet or below. So you can apply for a waiver to some of those rules, but you have to assure that you can mitigate any risks that you're incurring by doing that. So there are manufacturers that are starting to work on aircraft type certification, which would eventually allow flights over people, flights at higher altitudes, and there are a limited number of operators doing that right now. The industry itself, as you can see, we're on our way to 1 million drones that are registered under the FAA's rules. Recreational owners of these are probably lagging. There's probably, I guess there's an equal number that don't have registration on them, just based on sales of drones. It's required by law. It's hard to enforce. Commercial operators, it's in your best interest to follow the rules because there's huge fines that come with this if you violate it. So that's a fairly accurate number. And you look at it right now, there's 250,000 remote pilot certificates out there. So that's more than there are traditional aviation certificates right now. So it's a rapidly growing industry. So quick look at the range of capabilities that we talked about. So again, this is something that you can pick up from Best Buy for a couple $1,000s with the entire kit, bunch of batteries, and you can fly it for almost a half hour and get some great imagery and video. It's good for site documentation, lower accuracy orthomosaic. So when I say low accuracy, it's still pretty good for design. We're talking maybe 0.2 to 0.3 foot elevation. So you're not going to design an engineering off of it, but you could use it for 2 foot contours perhaps. A higher accuracy imagery capability like we have here with ours using a phase 1 metric camera. This will get you down to 1/10 of a foot or better accuracy, vertical. So you can start to get some pretty good contours. You get 6-inch contours from this. It's a little bit heavier as you see here, so it takes a bigger drone to fly it. We use this for detailed inspections and ortho photos. Give you an idea of what you can see with a 100 megapixel metric camera. We had this out on a project. We were testing it out to look at utility infrastructure to inspect insulators on high voltage transmission towers. In the background of one of the images, I saw a roundabout with a car driving around the roundabout, so about 300-400 feet away. I zoomed in and I said, I bet you can read the license plate on it. Not only could we read the license plate, I could tell you the registration on the license plate. So pretty powerful cameras. Just in comparison, this is a traditional DJI drone compared to a metric camera, and we're not even anywhere near zoomed in on this right here. So big difference in quality, much higher quality lens, so you're gonna be able to get accurate measurements from this as well if you pair that up with an IMU. On the LiDAR side, you're talking maybe a 40-pound drone that flies for a half an hour. If you tie this to a hybrid drone, gas electric drone, you can keep it in the air for an hour to an hour and a half. So, excuse me, a decent platform for getting colorized point clouds for engineering design, electrical utility infrastructure, watershed analysis, and so on. Show you some examples of this. thing to point out too, when we're talking high resolution imagery for mosaics, for LiDAR, there's still survey required with that. You need a set control to be able to tie things into XYZ space. So it's still a survey project. So just to get a quick video showing the metric camera in flight right there. So it's pretty decent size. This isn't a little one that you're going to fit in a backpack. So depending on the project, we often have a crew of people out there working on these, operating, especially in an urban environment, as a visual observer. So I'll give you an example of the scale of our LiDAR drone right there being set up. So common misconceptions about UAS, what it doesn't do. It does a lot of great things, but what it doesn't do is replace the need for a surveyor boots on the ground to help with your engineering project. It supplements your survey data. It's not the final thing that you're going to have. You can't run and gun with it. It takes some planning if you want to get good data, and you do need a set control. The post-processing of this data is just as important as collecting it. So after you've collected data, whether it's imagery or LiDAR, it takes skilled folks on the back end to get the most out of it and ensure that you're getting accurate data to support your project. So the principles and science behind the LiDAR and imagery, these all remain the same as they do with traditional methods of acquisition. The only difference here is we're changing how we get it using a drone. So things that go into planning a project, where is it? How big is it? What are we trying to capture? How are we going to set control? How are we going to fly it? All those things need to be known and determined if you're going to decide is UAS the right tool for the project. There are constraints for using UAS, bad weather. Obviously, you can't collect good data if you have rain or snow. Gusty winds can impact your flight. You want a stable platform. So we can fly in pretty decent winds, but there's a limit to that. If you're doing imagery for an elevation surface, a topo surface, or even LiDAR in some cases, vegetation can be impenetrable and you need to go in there and boots on the ground survey. Certain applications may require high accuracy or point density than we can accomplish with the UAS platform. So I mentioned the need to sometimes use a terrestrial scanner. Also, the regulations that we talked about are things that we have to work within. Give you an example, that is airspace. So this is the Madison area right here. And this shows you the airspace map for Dane County Regional Airport. So the FAA has designated boxes around the airport with a maximum altitude in which you can fly the UAS and get automated authorization. So we can go into an app, plug in where we're going to fly, and if we're in any of these boxes that allow us to fly up to that height, we're good to go. If you want to fly near the airport where you have a 0-foot box, or you want to fly at a couple 100 feet at one of these lower altitude boxes, you need to go in and get a manual authorization, which can take some time. You have to submit a plan to the FAA and have that approved. But it can be done. So this project right here is a site that we applied for authorization. It's Chicago O'Hare, you see in the north part of the image, the upper part of the image. So less than a half mile from the runways of Chicago O'Hare, in a 0-foot box, we were able to get airspace authorization to fly at 200 feet. So it can be done, and you get your waiver within a certain time frame, and you're allowed to fly your project. So there's planning involved. So what we typically do is start with our deliverables. What are we trying to get for our project, and determine, can we acquire that? What's the best way of acquiring that? Is it boots on the ground survey? Is it UAS, or are there other platforms we should be using? Can we achieve the accuracy requirements that the engineers need? Do we have the ability to fly it? Do we have the skill to fly it? There are some types of bridge inspections that we won't touch because it requires a level of skill that we haven't yet acquired. Whereas there's other projects that we're able to handle those no problem and do it safely. Do you have the ability to process the data on the back end? If you're going to fly a project, do the ground conditions allow you to get the best data that you have right now? So if there's snow on the ground and you want a topo surface, obviously you have to wait till the snow is gone. Likewise, if you have a forested area, you want to wait until the leaves are off the trees and you can penetrate the canopy much more easily. So there's a no-go process that we go through to determine if we're able to fly that project. Once you've determined you're going to fly a project, you have to do some risk mitigation to make sure you can still do it safely. So what we do is we identify all the things that can possibly go wrong on it, determine how likely is that to happen, how severe is the instance, how severe is that going to be if something does happen. And then we determine, can we mitigate that risk to an acceptable level, because Murphy's Law is always out there. Things go wrong, motors fail, batteries fail, planes enter your airspace. What are you going to do? So we use a process here where we quantify that risk based on that likelihood versus severity, and we take steps to mitigate that risk. So if we have an area where we have difficulty maintaining visual line of sight, for example, we will often use a lift to get a visual observer up in the air a little bit higher where they can maintain sight on the drone to keep safe visual line of sight on it. Then we use software to automate a lot of our flight planning. And that's going to be dictated based on what are we trying to do? Are we getting imagery, in this case, high resolution inspection imagery on a highway, or are we flying LiDAR? So LiDAR is very precise. There's precise maneuvers you need to plan on it. We're looking at correcting for altitude, and that would be a different flight profile than imagery. We want to set control on a project to make sure we can tie that into XYZ space and get good, accurate data. So these would be targets that we're going to put out on the ground that we can use post-processing. And the results that you get from this are some great data sets. So now that we have a background of how UIS fits into all this, show you some examples. This is some point clouds from our UIS sensor, or sorry, a LiDAR sensor. And we're getting multiple returns. So if you look at the image on the bottom, you're getting returns out. The first return is in orange. Subsequent returns up to 5 returns are in different colors. So we're penetrating into the canopy in this case. And as you can see underneath that spruce tree, we're still getting a surface on the ground because we're hitting it with multiple pulses per second. So that allows us to capture data beneath the tree canopy, whereas with an image sensor, a camera, you wouldn't be able to see it. So we're doing things like point clouds for mapping. This would be a mining operation up in the north where we're measuring quantities and depths in a quarry. We're in the bottom where we're looking at mapping infrastructure and utility corridor. So this was some image documentation of a substation that was built. More utilities infrastructure. This right here is where we had a video recording of, wait for it, there it goes. They detonated this area in a quarry right next to some high voltage lines. So they wanted to document whether or not anything was striking that utility corridor. We can get lines of sight before we even build a structure to determine, are we getting the view shed that we're looking at in this viewing platform, for example. This would be an imagery based solution. So this looks like LiDAR, but it's not. So if we have bare ground, we can use a low cost method to fly an image based sensor over it and use photogrammetry methods, aerial triangulation to pinpoint the XYZ location of, or XYZ position of any point in the image and project a 3D surface. And from that, we calculate volumes to a fairly high accurate level compared to having to have a survey out there, a surveyor walking on these piles, measuring points and then interpolating a surface. So we use this quite commonly on things like gravel pits and sand mines and in quarries. We have a large project starting in North Carolina this week where it's a mega site where they're building a large battery plant for Toyota. And they're clearing several hundred acres and they want to monitor on a weekly basis how much material is being moved around on the surface. And we're doing that using this method right here. So another example, that was sand mines. We also do structural inspections with cameras. This is the example right here, the chimney stack inspections. So the drone that you see on the left there, it's a cage drone inside of a ball that's flown manually without GPS that captures video throughout the inspection. So you could also use that in any kind of a confined space. asset inspections for utilities. Again, this would be one of the high resolution cameras. We're reading the manufacturer on an insulator. So we did that on 33 miles of core up in a UP this winter to help a utility contractor or utility client determine the various manufacturers of the insulators that were installed. So getting to the ones that are probably more relevant to folks in this meeting, using high resolution imagery to document reconstruction on a highway overpass in Milwaukee. So we're able to safely do this from a couple hundred feet away. So we're avoiding traffic. We don't have surveyors down in traffic trying to monitor and document this stuff. So we're able to get it at a safe distance. So you can see it's documenting the spalling and the cracking and the barriers inside the highway. This is another angle of it from the side. So this would be up high where it's difficult to access. And again, we're doing this at a safe distance. Another aspect of a higher value camera on that gradient level is a high dynamic range. So we're able to capture high contrast images and still get useful data. So this is the same image on both sides. It's just been adjusted to show the detail that was in the dark underneath. So even though it's a very shaded area, we're able to get good imagery of both the brightly lit area as well as the imagery of what's going on in the shade underneath. We can get 3D panoramas, so kind of like what you have with Google Street View, but we can do it up in the air. The LiDAR sensor that we use has two cameras along with the LiDAR sensor, so we have the ability to colorize a point cloud. So each point gets a value from the cameras in an RGB space, which also allows us to create an orthomosaic at the same time. So we can collect planimetrics from that data as well as a point cloud. So in this case, we're taking the ortho imagery and the planimetric data that was created from it. So we collect all this in a single flight rather than having to bring multiple aircraft and do this with multiple sensors. With LiDAR, the sensor that we're using can get you about 2 centimeters or better on hard surfaces. Oftentimes we're able to get 1 centimeter or better. This supports 1 foot contours. We can extract planimetrics from it, and it's used for site documentation and planning and design. Things like it's really good for corridor mapping, highway corridors, utility corridors, pipelines, topographic mapping, where it's very time consuming and costly to send a surveyor on 10, 20 miles of corridor. We can fly the entire thing in a day and then pull the data out afterwards. So things like vegetation encroachment, earthworks, agriculture, water resources, all these things can be done with this platform. So similar to the example I gave you with imagery, this can use LiDAR for it. The benefit here is we can penetrate a lot of vegetation and still get a good surface. So as long as light can penetrate it, we're going to see the bottom. So earthworks, like we were doing with the imagery-based sensors, we can get much more accurate surfaces using this technique compared to the imagery-based. And in this case, this is a point cloud for a transportation project where we're getting not only the ground surface and the topo, but also the utilities along it as well. So all those points of data were captured in a single flight. So rather than having a survey spend several days out there measuring all those things, we just capture it all and we can go into the point cloud later and extract the heights and the XYZ values that we need for a design. There are limitations though with vegetation. This was done in the summertime. And because we're only interested in the highway corridor, that was okay. But you can see off to the sides where it's blue, we weren't getting point coverage down to the ground. So if you needed that, you'd fly this leaf off. Another example would be for this landfill that we're looking at right here, where we're measuring subsidence over time. So from an engineering standpoint, this is much easier to accomplish with LiDAR than it is with a surveyor out there on foot. Corridor mapping for utilities. We're able to go in and extract features from this. So you can see highlighted in red are the poles, blues are the conductors. And we can extract features and get information now from this. So it's not just data and points. We can collect information to take measurements from it. So from a transportation and design standpoint, This is a 3D surface that was created from a LiDAR point cloud that gives you 1 to 50 planimetrics and the necessary topographic profile to cover, I think this was a 9-mile highway corridor, Highway 45. And that's used to do the final design on changing intersections, some of the other features that our civil engineers wanted to plan into the rebuild of this road. Another example of a project was a Highway 41 overpass project that we did, where we flew a couple of overpasses where they wanted to replace that overpass. And in this case, it's also running over a railroad crossing. So it's a high volume of traffic, and there's a lot going on this site where it was hazardous to surveyors on the ground in many locations. So by flying EOS parallel to the highway, we're able to capture data in addition to the oblique imagery that I showed you earlier. So there is a dead spot underneath. You can see with the blue on the bottom image. And the intent then is to go in just that little area under there with a terrestrial scanner. You can see it on the right image there where it's painting underneath another overpass, and we can fuse those data sets together. So high value traffic, you're not going to shut down lanes on something like that unless you absolutely have to. And we're fusing many different types of data together on a project like that. There's also agricultural projects where we fly with very high point densities to understand the structure and the growth and yield of different, this is some vineyards or some lemon orchards in California. A quarry in Chicago. So this is a very hazardous site, 300 feet deep, where it's just about impossible to survey it on foot, whereas a drone handled it very easily in an afternoon. Another site I'd like to highlight is this slope stabilization that we flew in California. There's a wildfire that went through, and then subsequently had a lot of landslides due to erosion. Lost the tree cover on it. The range from the top of the site to the bottom is over 1,000 feet. But by using LiDAR on it and just a couple of flights, we're able to, you can see the slope now would have been hazardous to survey on foot. Shows you the gradient in the profile right there. We're able to give the designers a very accurate profile from which they can design their erosion control measures in reconstructing the road that transects that site. So the image on the right looks like a photo. That's the point cloud itself. There it is again, the surface superimposed on the imagery. So that would have been, I don't know how you'd have done that with traditional survey. UAS is pretty much the only way you're going to do it. So very hazardous site, best tool for the job. So we could do that on a lot of different sites like that. This is a good tool. Water resources. This is a site in Madison that was flown with some former sewage lagoons that were converted into a wetlands area. So we're mapping it to look for subsidence in the berms. Stream restoration in Colorado. So again, mapping a fairly decent sized area with UAS and a couple of flights where I've taken a week in the field. An area in Michigan where a dam broke and they're looking at mitigating the risk from a future design standpoint. Where do they want to put a new dam? So we mapped a 500-acre site in a day and a half, where it was just about impossible to get out there on foot. So want to save some time for questions here. So again, there's a lot of things that you need to look at when you're planning a project, but UAS is often a good solution for that. Any questions? And if there's questions in the chat, I can't see the chat window, so maybe somebody can help me out.
Yeah,
I have a question.
Go ahead.
Can you hear me? Hello?
Yeah, go ahead.
So when you are deciding whether you're going to, say you're contracted out to provide a aerial survey for a, let's quantify it at 500-acre site, for the most part,
Oh, Broke up after 500 acre site.
This is best. Say that again?
You broke up after you said 500 acre site. I missed the rest of it.
Oh, sorry. I'm on the 151 in Wisconsin, not the best reception. But the so 500 acre.
Oh,
Oh, I'm not hearing you.
sorry. Yeah. All right, so
Yeah, so can you hear me all right, Paul?
Yeah, I hear you. Yeah.
Awesome. All right. So I got a question. You touched on water resources. And I was just curious on the accuracy of possibly mapping, like, say, riverbeds or creek beds. Is that possible? Is that even feasible? And how accurate is that?
There are sensors now that will penetrate water. I don't have familiarity with them enough to give you an accuracy measurement on it. It's something we're starting to learn a lot about. It's being used in a lot of places, and I'm sure there's limitations in the depth in which it can be used because the light still has to penetrate the bottom, right?
Right.
So, that I wish I could give you an answer on the accuracy of it, but I do know it's being used. So,
That's all right. Good research project for me then.
yeah, if you find out, let me know. There's my email.
so the Google Earth, we can see the ocean deep bottom, right? That must be done by sonar or something like that.
Yeah, bathymetry is typically done using some sort of sonar measurement, right?
Yeah, you cannot use
And deep water LiDAR won't work because light can't penetrate that far. So it's going to be, however far it can penetrate the water column, and it's going to be a factor of the clarity of the water as well as the depth. So with the sensor that we're using, water doesn't give you a return. So it's actually a good way to detect where the water level is if you're mapping a wetland. It just swallows up all your light.
All right, so a couple of questions in the chat. I will read it to you then. So how much are the survey grade drones?
So the LiDAR drone that we have, the drone itself is one component of it. And that the one we have right now is, I think it's about $40,000 or $50,000. A hybrid runs you about $90,000. It's the ballpark. So that's just the drone itself. Now you have to put a payload on it. So a high-end camera is going to run you with the lens $30,000 to $40,000. A LiDAR sensor, a survey grade LiDAR sensor is $200,000 and up. So I've seen them at $350,000 and up for a full-size VUX. You can get lower end, like I said, that asset grade. You can get something that's asset grade for less than that, and they're less accurate. But if you just need a general terrain surface, they're okay. But you're not going to do any design from something like that. So, yeah, the equipment's not cheap. It is coming down in price, but it's not something you go pick up at Best Buy.
I also have a question tied to that. With all those data you collected, you have to have software to processing it. Do you need to pay for the software as well?
Yeah, there's software licenses that go with it as well. So it really depends on your workflow of what you're looking to use. So imagery it could be as simple as something like Pix4D or Esri has Drone to Map. There's cloud-based services as well. Drone Deploy is one. So you could go get a Mavic, go fly it, and upload your data to the cloud. They'll process it for you, and you get an image mosaic and a terrain model when you're done. High-end survey level results, you're going to need some dedicated software for that. So trying to think of some of them that they use. Topodot, TrueView. We use TrueView software from GeoQ or Evo, TrueView Evo. I couldn't tell you what the licenses are on those. It's something an organization will have, an individual is probably not going to buy it. Probably more importantly is you need to understand the workflow behind it. So there's a learning curve on those as well, just like anything you're doing in engineering, right? So
another question very close to that. With all the data, with all those new technology, are we expecting all the civil engineers in the future have to graduate with a computer's coding background or capability?
No. The work that we're doing at Ayers right now, our geospatial division handles most of the processing for it. So give you an example. I get a request from somebody, they want to do a dredging project on Whitewater that was just done recently. And they want an accurate surface model within a certain spec. So we find the best tool for it. In this case, UIS worked. We flew it, processed it, gave them the surface. They could have had the point cloud with 3 billion points in it if they wanted it. But really what they ultimately wanted was a contour map, right? They wanted contours and a surface model. So we provide them the data set that they need to fit into their civil 3D project so that they could do the analysis that they needed to do. So the processes that you're already learning to use in your workflows as civil engineers, UAS just provides another way to collect that data that you can feed into it. So you could go and learn some of those techniques if you wanted to, but there are certified professionals that actually work in that as well. So that's why it's a team approach and the way we handle it.
Okay, all right. So I think this question ties to what you said there. For example, at your company, when you go out as a crew, right? You said that it's a collaboration. So what type of the people are in there? You need pilot, technicians, survey crews, and then who else?
Yeah, so our surveyors are actually most of our pilots, or the other way around. Most of our pilots are our surveyors. The way we view this is just another tool to collect data for a surveyor, right? We also have some geospatial technologists that fly them as well. So oftentimes it could be a one-person crew. Complex sites, it might be 2 or 3 people. Once the data is collected, we have different people that specialize either in image analysis or image processing or LiDAR processing that will go through and process that data. With terrestrial scanners, we have surveyors that handle that. They're very skilled at doing that. So there's different skill sets that come together depending on what kind of data we're working with.
Okay. All right. Any other questions from the house?
Yeah, I got it. Yep. So as this UAS system becomes more common, is there, in terms of job outlook, are surveyors going to someday become irrelevant when this data becomes more applicable, more common, or is there still a demand for surveyors in the industry?
There's a really big demand from right now. We don't have enough in the pipeline to fill the positions that the industry wants to fill. As far as UAS cutting into their job security, you know, somebody could have made the same argument 20 years ago when GPS came about, right? Well, surveyors are using different techniques back then than they are today. GPS is just another tool in the toolbox that makes them more efficient, more accurate. UAS is the same thing. So UAS isn't going to replace them. UAS supplements their skill set. And a skilled surveyor that can use all these tools makes themselves even more valuable. Or a civil engineering tech, for example, that can use these skills. If you can access the technology and provide it to an employer, in addition to the other things that you're learning, you know, you have all kinds of job opportunities in that case, or processing the data or wherever you find yourself within that realm. So, and again, remember, like I said in the beginning, UAS occupies a realm in between traditional survey and large scale data collection. So there are a lot of projects that UAS is either too big for or not adequate with accuracy or whatever. So it's just another tool in the toolbox. And the reason we wanted to highlight it in this presentation is so that, you know, young folks that are getting into the industry in civil engineering recognize that, hey, here's one more tool that we can tap into that might give me a solution to a problem that I have.
Thank you. All right, so a lot of questions from the chat box. For
Good.
open commercial sites, for large developments, for example, 100 plus acres, are you better off using LiDAR or conventional survey for cost? Are contractors hesitate in bidding flowing projects to vertical claim concerns? Do you add disclaimers to how the data was obtained in the bid documents?
We measure it to a certain accuracy standard. So if they want 6-inch contours, for example, we can achieve that. That's what we promise. If the vertical accuracy is expressed as 1 in 500 planimetrics, we design to that. Or if they need a surface within 2 centimeters on hard surface, maybe 4 centimeters on soft, whatever the case might be, right? We're providing an accuracy assessment to that standard. So how we get there, it's almost irrelevant as long as we can certify it's to that accuracy. So that's how we approach it.
All right, next one is, what is the limitation on how far a drone can go from the operator? You said you have to maintain it eye of sight.
Yeah, visual line of sight, yeah.
Can this be mobilized in a short time for emergency purposes?
It can be, and it has been done that public service. So police departments, fire departments, wildfires. The wildfire community has a huge aviation program, manned aircraft and UAS. As far as how far we can fly it, visual line of sight depends on the size of the drones. Little ones, you're lucky to see it at a half a mile. Our big ones, we can see 1.5 miles easily. If you incorporate a visual observer, we can go farther than that. So it really depends on the size of the drone and the terrain as well, right? So you go a couple miles. If you use, you can use dual controllers with a hybrid, and you can have them leapfrog each other. Where one's flying it for a mile, you have another pilot waiting a mile down the road. They can take control of it. They're flying it a mile. In the meantime, the first pilot leapfrogs down, and they can continue handing it off to each other. So there's ways in which you can make this maximize, what it's collecting in the air. The one we have stays in the air about 30 minutes right now and needs to come back for new batteries. So typically we can fly it 1 mile in one direction and 1 mile in the other direction. We're collecting data at 5 meters per second with the LiDAR scanner. So that's about how far you're going to cover in that time frame at that speed. We're going to be acquiring a hybrid here shortly, though, which will greatly extend our range.
All right, so another question, what app would you suggest to use to find out which airspace your project will be in? You mentioned about the app, let's choose you the FAA.
Yeah, there are several you can use out there. There's Before You Fly is one that the FAA has worked with a contractor on. AirMap is another one that you can use. We use that to unlock our airspace, so I don't advocate anyone in particular. Skydio, there's a number that you can use. So our pilots all use AirMap. We have an account under, they log in, and if you need to unlock airspace, that allows them to do it. Because we're pre-planning as well, if we're in controlled airspace and we need to do a manual authorization, we use FAADroneZone.com, and we apply for the waivers and authorizations through that. That has to be done in advance, though, because there's people in the loop on that one. It's not all done through software.
Okay, so there's one more question from the chat box. What education experience do people typically have when beginning to work in the U.S. program?
Boy, it's all over the place. So I mentioned we have surveyors doing it. There's folks with geospatial background like myself, engineers. So it's really, again, it's a tool for whatever your line of work is. I've used this for natural resources. I've used it for engineering. We've used it for a lot of different agriculture. I have Part 137 certification as well as Part 107 is the drone certification. I got Part 137, which is basically FAA's regulations for flying a crop duster. But if you want to fly a drone for herbicide application for planting trees, you need to get certified as a crop duster too. So we had to apply for waivers for crazy things like having a seatbelt on board, wearing a helmet, having a manual on board. None of that applies to drones, but the FAA has it in the regulations. So you got to get exemptions to all these crazy things. So one skill set, if you want to work with UAS, is you have to be a little bit of a lawyer to understand how the regulations work and how you can work within those and get your job done. So basic applications, it's pretty straightforward. And that's basically what the FAA's Part 107 certification to fly a drone is to know the rules and know how to read the airspace maps. It doesn't teach you anything about flying a drone. That requires experience, hands-on experience working with somebody else that can fly them. The simple ones are pretty easy to pick up yourself and learn how to fly. The big advanced ones takes a lot of hours to learn how to fly those safely. So being able to do it accurately as well. But getting a Part 107 certification, basically you study, most folks here can do it, probably 10, 15 hours of studying, go take the test. get 70% on a 60-question test, and you have your license. And then you have to renew that every 2 years. So it's a pretty low hurdle to get through if you just understand the rules. Gaining the skills to safely fly them is a different thing. It's more of a hands-on thing that takes time.
I'm going to try my question again. I'm in better reception.
Yeah, it sounds better.
Yeah. So say you have like a 500-mile or 500 acre, mostly linear corridor you want to survey. What is the threshold where you decide you want to use a UAS system connecting to RTK with some supplementing with a little bit of survey and or a LiDAR system with survey? And let's say the accuracy you're shooting for is, I don't know, between 3 and 6 inches.
RTK could get you that. You know, we typically don't do that because we're usually using it for higher accuracy for our designs. Caution you about not using any survey. There's a lot of people that try to claim they can get it without any control. How do you know how good your data is when you're collecting it, right? Without any kind of control, you need to have some on there. So the threshold on that, yeah, anything below that 3 to 6 inch accuracy, you're going to definitely want a little bit more control on it. So on a site like that, what we look at on a corridor is typically we want maybe 2 points per mile. So it's not a huge burden, really. So, and there's options out there for quicker survey too. We don't do it, but I know some firms, they have portable targets that have survey. I don't say survey level GPS because it's not quite survey level GPS. Certainly asset grade GPS embedded in the target. So you just go out ahead of time, lay those targets down. They're collecting data while you're flying and recording the points where they are. And you can use that. So that's a way to speed up your control. And then you can move those targets.
About the propeller arrow points there.
Yeah. Yep.
Yeah,
So
no,
there are
I
other
was just
solutions you can use. We don't use them, but I know some folks are using them. I'm looking into them. I'm certain, like what you're saying, is sort of a compromise in some areas where maybe you don't need quite as high of accuracy.
Yeah, I've had good experience using that platform before. But in terms of a survey using, let's say, like a Phantom 4 RTK supplemented with a high amount of ground control and checkpoints and things like that, do you think that accuracy level is attainable, or basically at that point you should go LiDAR?
If you're trying to get down to 1 inch, 1/10 of a foot, yeah, you probably need LiDAR or a metric grade camera. So we've compared the two, and we can't typically ensure 0.1 feet accuracy with that level of drone.
All right.
It's a combination thing. Smaller sensor, small lenses. You start getting more aberrations in the lens or mass produced, right? So we don't have exact tolerances known in those. So it's a little bit harder to get high accuracy off of them.
All right. Okay. So I'm going to pause here. So 6 o'clock, I just want to make sure the person here, both in person and online, it's 6 o'clock. So we are officially end the seminar, but we will stay here until we finish all the questions and then the discussion. So if you have things to do, feel free to leave. Thank you for coming. I will send you emails about how to get your PDH. But other than that, thank you for your time. And then for the in-person one, sorry, I missed the chance to get the cookies. But I will do next time. Again, let's thank our speakers. Again, I believe the speaker will be here to answer more questions and more discussions. Thank you very much. Thank you.
Thanks for your time.
All right, so feel free to leave. Otherwise, we'll stay here for more questions if we have any. So, yeah, for the Zoom attendees, feel free to unmute yourself. Yeah, I'm gonna stop recording first.